right, so last time we started this section about integer addition and subtraction, and we looked at two different models that were almost the same, right? They were this idea of doing charged values, the positives and negatives in a circle, and the idea of doing a chip model, which is doing a black versus a red chip in a circle as well. The third one we're going to look at is a number line model, which is also very commonly used. And you've seen number lines done before. I'm going to just draw one this time. But we've got a number line. We're starting at 0, and the first thing it says is I want 5, so I'm going to count over to the right 5. And I'm going to draw an arrow. Typically, I will draw it above just to distinguish it because it starts to blend in if I don't have colors anyway above the line. So this is the number 5. And this says plus -3. Well, actually, that looks a little bit funny, but -3 is going 3 in the other direction. So from wherever I ended up, I would go 3 in the opposite direction. So that's -3. And where do I end up? What is this spot right here? 2. So this would be my example of a number line model for 5 plus -3. So negative is indicating that I'm going backwards along the number line. All right, a pattern model is a little different. So it's kind of difficult to describe exactly where you start on this, but you should start at least back with positive numbers. So we're going to go back here and we're going to example, we'll do 5 plus 4. Nothing special about starting at 4. But what is 5 plus 4? 9. Okay. My goal is to do a pattern until I get down to 5 plus -3, so I need to decrease these numbers by 1. So what is 5 plus 3? And 5 plus 2, and 5 plus 1, about 5 plus 0, 5 plus a -1 then, and so here's where the pattern issue comes into play. So everything else we did when we did addition and subtraction of whole numbers. But once I get to 5 plus -1, I've got an integer involved, and the pattern is what's happening here, 9, 8, 7, 6, 5. So by patterns, this has to be 4. Even if you didn't have the concepts that you understand of working with addition and subtraction, okay? This is the pattern of what's going on. It's kind of like what happens when a child learns their multiplication tables. First thing they do is they learn about the pattern of the table. So if I look on multiples of 3, or actually multiples of 5, so it's a good example. Because we work on multiples of 5 people, what we'll get in first grade, we're doing nothing with multiplication. They know they're counting by 5s, right? 5, 10, 15, 20, 25, 30, and so forth. But they don't yet make the connection that 5 times 3 is 15, right? They're doing it in a patterned way, and that's what's going on here. So I have 5 plus -1, -2, and I get 1 less 3, -3, which is the one I was wanting to get, and I get 2. And once I get to where I was wanting to get, I'm actually done. And so by a pattern analysis, this is 2. Okay. So you might be asking or thinking, but how do I know that I need to start at 5 plus 4? Well, you don't have to start with 5 plus 4, but you do have to have a couple of examples in here where it's 5 plus a positive number. Otherwise, there's no pattern that you've established to proceed with. Make sense? So you would at very least need to start right here at 5 plus 2. This would be my minimum starting spot to give me a pattern established properly. All right, absolute values. Tell me what you know about absolute values. What's an absolute value? Good. We don't know anything about absolute values. All right. All right, well, they look like this, right? You guys remember the notation? I've got vertical bars. The easiest way to describe an absolute value is that it's a distance. And distances are always positive. I don't have a negative distance. It doesn't take me -4 miles to get home, right? So it doesn't work that way. Well, we have one of two options. The absolute value is either equal to what it's equal to begin with, or it's equal to the opposite of what it began with. So ignore the second one because that's a little bit more to take away with. But when is it that the absolute value is just equal to the number inside? Remember? Say it. There is no negatives here, so I don't have any negatives at all. Okay, absolute value of x equals x. What's that?
Never mind.
Okay, I think maybe you guys need numbers because you just look at me like you don't know what I'm talking about at all. What's the absolute value of 5? What's the absolute value of negative 5? What's different? Why in the world did the first one stay the same and the second one change signs?
Isn't it because it's like the distance from 0?
Okay, that's what an absolute value is. It's a distance, which I was going to get there. Let me write it down now since you mentioned it. This is the distance from 0. So when in the world do I just get to remove the absolute values and do nothing else to the number? When it's positive. If the number inside the absolute values is already positive, then I don't have to do anything else. I just take the absolute values off and I'm done. So this right here, this first one, is when x is greater than 0. Now, this does not say that my answer is negative. It kind of looks like that. That's not what this says. You see, what happens here when you did absolute value of negative 5 is that this negative here means it's the opposite of the number inside. That's what negative means. It means the opposite of. So when I have a negative number and I take its absolute value, I need the opposite of it. And the opposite of it would be, in this case, positive 5. Okay? So I have this sort of idea of change. This means change my sign. Or it means opposite. It doesn't mean negative. Okay? It doesn't mean I'm going to take a number and I'm going to get a negative distance. That is not what's happening. But this is going to happen when x is negative. And I guess in theory, you could probably put an equal sign up there when x is greater than or equal to 0. This happens when x is negative. This is all about the distance from 0. And I wanted to draw you a picture about that since Megan brought it up too. But it is in my notes. If I have 0 here, and I have the number a over here, this distance is a. That's how I plotted it anyway, isn't it? I moved over to the right 7 or 12 or 2 or whatever. So that's a distance, okay? If I had a number over here, say that this is b, that b value already is a negative number, isn't it? Because it's on the left-hand side of 0. It is negative. So this distance right here is not b because b is a negative number. This distance right here is the opposite of b. Whatever b was, it's negative 77. Well, the opposite of negative 77 would be positive 77. So that distance would be the opposite of my number is running with, so it would be positive 77. Are you okay with that? I think I have an example, next with that in there, that idea. All right, so we do this from time to time to think about whether or not we understand the actual wording of what examples tell us to do. This idea of creating true or false and deciding if it works all the time, whatever. When I have homework to pass back, don't forget about last time. All right, so the first one, part A, says we want to know if the absolute value of x squared is always equal to x squared. Why, Kaylee? You're pretty certain.
Because no matter what x is, even if x is a negative number, like once you times it by itself, it will be positive.
Yeah. Anytime you square a number, whatever that number was to begin with, which is what Kayla was saying, it becomes positive, right? So x squared is a positive number. By definition, if I have an absolute value of a positive number, I just remove the absolute value signs. Does that make sense? The issue is, I'll write down a little bit. This doesn't ask me to do this, but I feel like you're not writing, so if I write it, you will. X squared is positive. So the absolute value of x squared equals x squared. That's by definition. How about x cubed? That is false. And the easiest way to show that something is false is not to make an argument about it, but it's to give me an example. Can you give me an example of when this would be false? Negative 3. Do you want that to be x?
Yeah.
Okay. So if x equals negative 3, then I have negative 3 cubed inside of an absolute value. What is negative 3 quantity cubed? It is negative 27. What is negative 27 absolute value? 27, right? But 27 does not equal negative 3 cubed, because negative 3 cubed is negative 27. An actual example of why this is not going to work. Easiest way. If something's false, show me an example why. We can call those counterexamples. Absolute value of x is non or not negative. Is that true? That is true. Absolute value of x is positive. Value of x is the absolute value of 0. 0 is not positive. It's not negative either, right? That's why part C works just fine. The idea that this value is a non-negative value is okay. But there is an example of a case where it's not positive either. That's number 0. Are you with me? And 0 is one of those weird things because it's not positive or negative. All right, we're going to go through a little bit more because it's in your book about the idea of our different properties. Let's just remind ourselves what they are. There's not a lot in terms of questions on these in your book, but we're going to get back to questions on these since we've done them before. Consider this a little portion of review, okay? Closure. What does closure mean? Equals a whole number. Okay, so it's the idea of combining a set, or combining two numbers from a set and still being in a set. So this is an example. If A and B are integers, then A plus B is an integer. Right? Here are two integers and you add them together, you get another integer. I can't add two integers together to be a fraction, right? No. This is why we do integer multiplication or addition with our children first before we start talking about fractions, right? Because they know there's going to be an integer and then we're familiar with it. Commutative. What does commutative mean? Oh, I have already written the A, B, or C or integers here. What is commutative?
Sorry, it doesn't matter.
Parentheses is associative.
Isn't that where you can like switch the numbers, like 6 plus 4 equals 6?
Right. So A plus B equals B plus A. It worked for whole numbers and it works for integers too. Associative is what Kayla mentioned. Parentheses. Give A plus B in parentheses plus C. This equals A plus and B plus C is in the parentheses on the other side. So the parenthesis grouping changes. That's all addition. You know what the identity property is? Not 1. 0. Yeah, so we got the 0, right? So that 0 is the identity. So if you take 0 plus A or A plus 0, you get back A. This one's a new one. We've not had this before. Whole numbers we've not had to add to the inverse property. So this is new. The additive inverse property, actually, yeah, we didn't have it. Let me say that way. Yeah. The additive inverse property says that if you have an A, then there's another number that is the opposite of A. So when you add them together, you get back the number 0. And it wouldn't matter which order you did that. So we could take negative A and then add positive A, and that would be 0 as well. I don't think I did that though. That's middle. so you know this, right? What do I have to add to 7 to get back to 0? Negative 7. What do I have to add to 43 to get back to 0? Negative 43. And we can do that with integers now because we have negative numbers. We didn't have negative numbers with whole numbers, right? Whole numbers are only positives, so there wasn't a way to add to it with another whole number and get back to 0, unless you were already to begin with. So we have this idea of an additive inverse now. All right, a couple of different things, properties that I want to make mention of. If you have numbers A, B, and C, the first one here is that A, let me write it differently. The opposite of negative A is what? That's positive. Okay, you guys remember negative, we think of it all the time in multiplication here. Negative times negative equals positive. Think of it like that. Think about negative as being changed in directions. If you change directions twice, you're going the same way that you started. Right? So go up the stairs, turn, go back down the stairs, turn, go back up the stairs, back where I started. B, if you have two numbers that are the same, maybe just different ways of writing them, like 3 and 3 times 1, or something like that, then if you add a number to one, it will be the same as if you add a number to the other one. And you use this all the time when you solve equations. Algebra, right? The idea that I'm allowed to take an equation and add a number or subtract a number from both sides. This property. Here's the third one. You have negative A plus negative B. This is equal to the negative or the opposite of A plus B. In other words, negative 5 plus negative 7. I could just say what's 5 plus 7? 12, and then I can put a negative in front of it. Instead of kind of combining like terms because they're both negative, they can be combined. And then the negative applies to both on the outside. All right. Did everybody get that? Did I go too fast? All right. Definition of integer subtraction. We've seen this before, but we haven't seen it for integers, so let me write it down. For integers, A, B, the value A minus B is a unique integer in such that A is equal to B plus N. Before I leave this one and go on to here, this is one of the ways that kids learn to subtract. They say 5 minus 2. And they say, what would I have to add 2 to get back to 5? It's 3. But so they think of it more like this. 2 plus something equals, sorry, yeah, that's right, I wrote it. 2 plus something equals 5. What is the something that's missing? What's that missing part, which we talked about this before. But it works for integers just like it works for whole numbers. All right, one more. And we use this all the time, and I've probably already used this even on the board today. Subtraction is really just adding an 8. I remember this usually being in 7th grade, algebra, or algebra 1, or whatever it was like that, whatever class it was. We were going in and our teacher telling us there's no such thing as subtraction. There's such thing as subtraction. All addition. Addition. Add never applies. No such thing as subtraction. It's all adding negatives. And in theory, okay, that's fine. But there's any missing thing. Okay, so addition of a negative and subtraction are the same. All right, so let me show you a model for, again, we went through these models. Let me show you what happens when we have negatives involved, because they do appear a little bit differently. This says 5, so start with a chip model, which is a circle. 5 means I have 5 chips inside. This notation right here, I understand that I just told you that the negative and the negative are positive. But I want to show you why that's true from a chip model. Okay? So I'm not applying an abstract idea. I want to actually show why it works. Because I will tell you what, I have a brother-in-law, and he took an algebra course as a college student. He was an older adult college student, you know, like his mid-20s, not his 16 or not 18 or something like that. So he was a college freshman, but he was in the middle of his 20s. And he had the most difficult time of understanding why negative and negative combine are positive. He couldn't figure it out. This will help with that idea. This right here means take away, right? We've encountered that idea before. Subtracting means take away. So this could be read as though I have 5 and I need to take away negative 3. The problem is this picture doesn't have negative 3 in it. All it has are positives in it, right? So what we're going to do is we're going to add negative 3 to my picture. Oh, I need the wrong color. But I can't just go adding values inside here that didn't exist before. You see, I need the negative 3 to take them away. But I have to add 3 to it as well in order to keep this whole thing still worth 5. This expression is another way of writing the number 5. Are you with me? This is 5. Because I have 5 here, 3 more here. This is the number 8 and negative 3. What's 8 minus 3? 5. This picture represents the number 5. Yes? Okay, well, we did it last time and you guys didn't have any trouble. This picture right here represented the number 2, didn't it? Normal green lines. I had 5 blacks, I had 3 reds, and this number was 2. What's next? Yes? This is the number 2. 5 blacks, 3 reds, red and black combined to be number 0. This is the number 2. How else can I write the number 2? I think I got to stop here for a second because you're still looking at me like a deer in headlights. So obviously I could write 2 like this. How else could I write 2? What other picture would be equivalent to 2? 4 blacks and 2 reds. That's the number 2. 4 blacks, 2 reds.
So for the one that we just looked at, like in order to make it 5, like we have to make it 8 first, the negative 3.
The one we were looking at, what I want to do, let me do one more step so you can see. What I want to do is I want to take these 3 and add and remove them. And the reason I want to remove them is because it says I need to take away negative 3. Well, reds are negatives, so when you take away negative 3, I've got to have negative 3 in there to take away. When I originally knew the problem, which is 5 blocks in there, I didn't have any negatives in there to take away. They weren't there. So in order to take them away, they have to be there. And they weren't there to start with.
That's why we added the 3 blacks.
Yes. We added the 3 black and the 3 red because I need the 3 red in there. You can't just go randomly adding extra pieces to something that doesn't work. Yeah. This would be like, okay, here's your equivalent. You guys remember solving equations, right? I know you do. This wasn't that one. To add 5 over here, you can't just add 5 once that equation. That is completely and totally inappropriate. What else do you have to do? Just add 5 over here. It's compensating to keep the balance that was there to begin with, right? There was one point in algebra as well where you did something like this. You added 5 over here and you subtracted 5 over here at the same time. You did it when you did something called completing the square. So you did it. Okay? That's the idea that we're doing here. In order to keep the picture, the inside of this picture, to be equal to 5, I want those 3 reds in there. But in order to get those 3 reds in there, I have to compensate by putting an extra 3 black in there as well. Okay? Now I can remove the 3 red. Okay, so in essence, this picture now became this. What do I have? I have justification for how this became 5 plus 3, which gives me 8. Let me do the charged one as well because it's almost identical. This says I need 5 pluses to start. There's my 5 pluses. I need to take away 3 negatives. There aren't 3 negatives there to take away. They just don't exist. So in order for them to be there to be able to take away, I have to put them in. But if I put 3 negatives in, well, that didn't work. I have to compensate by putting 3 positives in so that the whole expression is still 5. Now I can remove the 3 negatives. I'm left with 8 positives, and my number is 8. Okay? Let me do my number line model for this. I just stop here and I'll press that on Facebook. I guess I could put it on Facebook, but some of you don't have access to my stuff on Facebook. So here's the idea. All right, so we've got 5 minus negative 3. Here's 0. 1, 2, 3, 4, 5. Okay, so this is where we were before. This idea here, a negative and a negative, in terms of a number line, means what? It means addition, but what does it mean in terms of a number line? What happens when you do a negative on a number line? You go back the other direction, right? So here's what's happening physically. Watch me. Okay, so I'm right here, and I take 5 steps forward. And then I'm supposed to turn around, so that says subtraction. First negative. And then what's it say next? I turn back around again, and then I go 3 more. Okay, the 2 negatives in a row have to do with direction changes. But if you change direction twice, well, they waste harder, right? So picture-wise, you have this. It's the idea of changing direction. So when we're thinking about a number line model, we're thinking about this idea of changing direction. Let me do the pattern model. You know what? We're going to finish. We're just going to give me just 1 extra minute. Pattern model. We're going to start with 5 minus 2. What's 5 minus 2? 3. Thank you. 5 minus 1. 4. 5 minus 0. 5. So what's happening? My numbers here, the answers, they're increasing by 1. So what's 5 minus negative 1 then? 6, because I'm supposed to continue the pattern, right? So 5 minus negative 2 would be 7, and 5 minus negative 3 would then be 8 from a patterned perspective. Last slide. You guys remember PIMDOTs? Please excuse my dear Aunt Sally, so you remember it that way as an acronym. This is an order of operations issue. What does the P stand for? Not please. Parentheses. Parentheses. And this really means the stuff inside them. So if there's anything to simplify inside a set of parentheses, that's what you simplify. Somebody's already telling me E is exponents. So after we deal with simplifying the insides of parentheses, we should do anything that has an exponent on it. Then we should do, okay, so M and D I wrote here beside each other because you've been led to believe that it matters on their order, and it so does not. Multiplication, division. You move left to right. Okay? So if you've got division before the multiplication, it's great. You do the division first. Division and multiplication happen at the exact same time, moving from left to right. Same thing with AS. AS is addition, subtraction. Again, there is not an order to this. It's a left to right issue. And there's not a lot in your text that has to do with this, but it comes up in here, and there are a couple problems that have applied order of operations, so I wanted to remind you of that. Okay? All right. We will, I don't think that's what I need to do. We will have class again on Monday, on Friday, or before. It'll be before, because it'll be tomorrow. What do you have to do? You need 2 things, actually. This homework, so the group work and the homework here, all of it are assigned. And there's extra credit, that's what Katie's saying, right? The extra credit survey information I sent you guys, everybody knows what I'm talking about? What else though? One more thing. You should download the smart board, okay, we're just
Watch your
There will be another video out there for 5.2. The last section of the material. The last section of the whole semester. Yes, Charity?
So 5.1, 5.2, do Monday.
5.1 and 5.2, you need to do them by Monday, but I won't collect either of them on Monday. We will do questions on Monday, okay? So if I collect either 5.1 or 5.2, I will collect them the day that you do your test. All right, so you can do any questions on Monday. If you wait till Monday to do this, it's not going to be good, because you're not going to be able to ask your question. Oh, homework. Let me get what you guys are doing. If you have questions, please let me know. Lauren. Rachel. Sarah. Marissa. I know that. Yes, I got another star. Yeah. Yeah, just a second. This wasn't stopping for me before. I don't know why. think that I'm okay with you doing that, no problem. That we had that discussion before, whether you should be able to get some information. And we can do that if they allow it, but it's conditions.
Okay, I'll see what I can do.
Okay.
Thank you.
You're welcome.